Vladimir Dotsenko from
Dublin.
Dublin, sorry. And he changed the title of his talk. So it's right there. Homotopy, meaning of the Givental group.
Thank you very much. It's a great pleasure and great honor to be here. So I am really grateful to the organizers for inviting me. I also want to apologize to one of the organizers for telling things that he already knows of. So this is a report on some ongoing joint work with Sergei Shadrin and Bruno. This workshop is really great. I think that actually the first workshop I ever attended properly as still as an undergraduate student was a workshop here in Cambridge for the closing workshop for the program on symmetric functions and McDonald polynomials quite a few years ago. And these two workshops actually have one very important thing in common. It's absolutely impossible to pick a talk to miss. All talks are really exciting. I was quite tempted to miss this talk and to get some rest, but in the end, yeah. Right. So let me formulate the main result I'm going to discuss and say already right away that my main goal would be to just explain all the words used to formulate that result, and to make it a little bit more structured, I'll write down this main theorem, format it as a poem with some very strange formatting with different parts and different lines. So the main theorem says that the Givental group action on hypercommutative algebras is the gauge symmetry action in a certain Lie infinity algebra. So this is essentially the plan of the talk. I'll remind you what hypercommutative algebras are, what is the Givental group actions on hypercommutative algebra structures, what is gauge symmetry Lie infinite algebras, and how to construct a particular Lie infinite algebra which allows us to interpret the given type action. Right. So since this workshop is to an extent about operads, let me list some operads and operad related things which would be the main characters throughout this talk. So the geometric objects that will show up during the talk are the moduli spaces of curves of genus 0 with marked points. Both the open and the closed moduli space will play a certain role. And also two other geometric objects which are important, at least behind the scenes, are the operad of little disks and the operad of framed little disks. And the related algebraic part of the story is the operad of hypercommutative algebras, which is the homology of this guy. The operad of gravity algebras, which is the causal dual of this, and so both of these operads are causal. This is this was established by Ezra Getzler some almost 20 years ago. Yeah.
18.
Yes. And from as we all know, homology of little disks is the Gerstenhaber operad, and homology of framed little disks is the Battalion-Wilkowiski operad, and these are the four operads that are. So I think I will just denote the Gerstenhaber operad by G and BV. So these are the things that will play certain role here, and somehow, so the operad, in particular the operad Haiton, is the homology of the operad of genus zero curves, Deligne-Mumford implications of genus zero curves with marked points, and algebras over this operad are hypercommutative algebras, which sort of covers the second line of that statement above. Now, what is quite remarkable about this this type of algebras is that if you take if you fix a vector space V and try to classify different structures of hypercommutative algebras in V, it turns out that there is a fairly big group that acts on these kind of structures. Of course, when you study when you study structures of an algebra of a given operad on a vector space, of course you have some group actions. You can change coordinates in V and so on. But what is special about hypercommutative algebras is that there is an action of a large group which is somehow universal, doesn't depend on V, and it is always there. And so my next goal is to explain to some extent what this is. It will inevitably be somewhat sketchy, but for details you can look at the video of a talk that Sergei Shadrin gave here in February about the Givental group, where he also discusses various applications of it to working with intended to work with matrix models, intending to work with integrable PDEs. So there are various instances where this group action actually can be used to understand something. But and this group action, in principle, can exists in a much larger generality than I will need it in this talk. So it you actually can define an action on algebras over the modular operad where you include all genera, and then, of course, to have a structure of an algebra of a modular operad, you take a vector space with a scalar product and so on. But what is important is that action, which exists in a larger generality, actually restricts to genus 0, and that is the only thing that I will need. So. So the structure of a hypercommutative algebra is, since there are algebras over this operad, which such a structure amounts to a morphism of operads from this to the endomorphism operad, and I will instantly make some identification instead of looking at morphisms from homology into the endomorphism operad. I shall dualize things and view such a morphism as a homology class with values in the endomorphism operad. And so this I replace by just dualize, and so I view such a structure as a collection of homology classes which are sort of spread across homological degrees with values in the dimorphisms, and the property of being a morphism of operads means that these cohomology classes satisfy a factorization property. If you move to a boundary divisor, then you should have a certain factorization, the most obvious factorization you can think of. And this, under this identification, I will start drawing pictures to encode this sort of data. So such a thing with n inputs and one output will mean precisely this homological class with values in the morphism. So this thing, it has the part coming, the part that lives on the moduli space, and it also has a decoration which is an n-ary operation on V. And now, so the Givental group is the, let me say the Givental linear algebra, which will be a pro-nilpotently algebra, so then we can easily exponentiate it to a group, is so you take formal power series without the constant term with values in NV of 1, which is just the linear again, this is one of this is not the precisely the Lie algebra that and Lie group that Givental worked with in 2001 when he defined something in order to in order to prove various things, in order to prove the Virasoro conjecture in Gromov-Witten theory and so on, since he was working in that larger generality that I mentioned, and essentially was working with algebras over a modular operad, so there was a scalar product, there was some extra data, and therefore he would use not all linear operators in V, but linear operators which somehow agree with the scalar product. But it turns out that that can be generalized if we work in genus 0. We don't really apply the forgetful functor. So if we don't work with modular or cyclic or whatever operads, but we just work with normal operads and we drop the scalar product, then we don't need to make any assumptions on the kind of operators that we use. So now, if we have some power series R of Z, like belonging to that Lie algebra, let me write down formulas explaining how to deform infinitesimally a hypercommutative algebra structure using this guy. And then to deform genuinely, you just need to exponentiate. So this traditionally, I'll write R hat, meaning that it is some, so it is some action that we define. So it's since R lives in linear operators in V, of course it can act in some naive way on endomorphisms, but it's not what I want to do. So and now I'll draw these pictures, and I'll need to look at my notes to make sure I tell you the correct signs. Let me actually, since I'm dealing with Lie algebras, I can just define it on individual monomials and then extend by linearity, and everything will work wonderfully. So I will write a formula and then explain what these terms actually mean. Yes, that is okay. As I said, pictures like that, they live on they have parts that live on moduli spaces of curves and parts which are multilinear maps on V. And for instance, so some ingredient which is in these formulas which I haven't defined yet are psi classes on moduli spaces of curves. So on the moduli space of curves with n marked points, you have n obvious way to define a linear bundle. You can look at the one of the marked points and look at the tangent line to your curve at this point. And so there are if you take point number k, you have Lk, the linear bundle whose fiber at a given curve is the tangent line over the kth marked point, and the corresponding psi classes are just the Chern classes of these bundles. So now,
bar or
well, yes, I explained for simplicity how to define it on the open moduli space, but it extends to a closed moduli space, so it actually so, for instance, the meaning of this first symbol is that you take this gadget, which has the part that lives on the modulus or in the which is a homology class modular space, and the part which is an n-ary operation on V, and you the part which is a multilinear operation on V, you can precompose with your linear map R, which makes perfect sense, or maybe post-compose rather, and the part which is a homology class on moduli space, you can multiply by the kth power of the psi class corresponding to the relevant marked point. So this formula makes perfect sense. This is also perfectly fine. Here we move a little bit further. Here we this guy is made up of two pieces like that. So this means that you have this picture, strictly speaking, lives on the boundary divisor of the moduli space, and you need to use the push forward on the cohomology to actually make it live in the same place where these two guys live. But also you do exactly the same. You multiply by the ith power of the psi class corresponding to this marked point, by the jth power of psi class corresponding to this marked point, and in between composing the two operations, you insert the linear map R. So at least this formula makes sense. And what is not immediately obvious, or not very obvious at all from this formula, is that it gives an infinitesimal deformation of the hierarchical commutative algebra structure. So up to in the first order, it really the corresponding new deformed cohomology classes do indeed satisfy the factorization properties still. But this is indeed true. These formulas did not appear in the original work of Givental, but since then, in many places, these formulas were obtained, and it was indeed checked that they work well. So in one of the papers of Yangping Li and in an unpublished work of Maxim Kazaryan, in some sense, I guess, in one of the papers of Konstantin Telemann, this.
But these formulas are in Givental's paper. I don't understand.
Well,
They're written down in a generating function. They're not written in your notation, but they're written in his notation.
well, yes, but
I mean, what's the point you're making? That if we want to look for these exact ways of writing it, we should look in YP Lee's paper. Is that your thing?
I guess.
Yeah.
I guess. Yeah. No, I mean, I guess yes. I guess the point that I'm making is that for me, as more of an algebraized translation from Givental relation to this was non-trivial. But yes. Okay, I'm willing to believe you on that.
Or it doesn't use anything. You know, it's pure theory.
And if k is greater than n, what was the
Uh,
k is greater than n?
Well, there is no problem. It works for it's just that if k is large enough, if k is greater than the for instance the dimension of the moduli space, then of course the power of the psi class will be 0, and so. No. This is not an index. This is power psi to the power k. I suppress the index because I always write the psi class next to the point to which it corresponds. Yeah. Right. So this is this action, as I said.
The last term, I'm sorry, is it on purpose? I mean, there is a choice. This output to what input to join? Is it the sum of...
No. It's just the first one. Just the first one. Yes. Right. Now let me. I said already that this action can actually be used for various purposes, but I don't really have time to elaborate on that. And let me rather explain how, for a humble algebraist like myself, these formulas, which look somewhat mysterious, can be sort of demystified and put into the context of homotopical algebra. So for that, I need to move to the third line of the statement, to gauge symmetries. And in that part, I'm essentially reminding you one small part of paper by Ezra on Lie theory for nilpotent Lie infinite algebras. Namely, so let L be a Lie infinite algebra. Indeed, I need to, for formulas that I will be writing to make sense, I will need to assume that it is nilpotent in some reasonable way, but I wouldn't specify for now in what way. Just believe me that for formulas that I will be, for the Lie algebra to which I will apply it, these formulas will make sense without any doubt. So let alpha be a Maurer-Cartan element, meaning that the Maurer-Cartan equation for linear infinity algebra holds, sum over n1 over n factorial ln of alpha alpha and so on alpha is equal to 0. Now let x be an element of homological degree 0. Well, before that, I guess I should say that using a Maurer-Cartan element, you can twist the Lie infinity structure and define new on the same vector space L. Define a new Lie infinity structure Lk alpha with structure maps Lk alpha. Where you sum over all p, so you take an old operation, insert p copies of alpha and the arguments on which you want to compute the operation, divide by p factorial and sum. And because alpha is a Maurer-Cartan element, these new operations will satisfy the Lie infinity axioms. And now, similarly to how it happens in the case of DG Lie algebras, where you where you can use the degree 0 elements to define the Lie groupoid to act on Maurer-Cartan elements, you can do it in this Lie infinity setting.
Assuming that the negative degrees are 0.
No, I'm not making assumptions of that sort. So if you take x and L0, then the element and alpha still being a Maurer-Cartan element, then L1 alpha of x provides you an infinitesimal correction along the Maurer-Cartan variety. So if you change alpha by this element, you get something which is in the first order in epsilon still a Maurer-Cartan element. So you can write you can look at this vector field and integrate it, and this somehow explains you how to move from alpha in various directions for various possible x. And somehow in the general Lie infinity context, this generalization of the Lie groupoid will rather be an infinity groupoid, so there will be the story will be more complicated. But somehow in the example that we shall discuss, it turns out wonderfully that we still have just a groupoid, and the corresponding action will somehow give us the Givental action. And now, so is a Maurer-Cartan element. epsilon. So these guys for various x in L naught are infinitesimal gauge symmetries of Maurer-Cartan elements. And if you then you can integrate them and obtain something which is natural to call gauge symmetries of Maurer-Cartan elements. Right. So now I'm left with the fourth line of my statement, where I promised you to construct a certain Lie infinite algebra where it all will be happening. And this is going to be fairly interesting. This relies on, in the first instance, on the joint work of Bruno with Andy and Ima, who constructed a model for the operad BV using inhomogeneous causal duality. This model is not minimal. It was made into a minimal model. From this, a minimal model was obtained in joint work with of Bruno with Gabriel Drummond Cole, and somehow right now I want to remind you a bit about how this works, because our Lie infinite algebra will be constructed from that minimal model, and there is some magical feature of that minimal model that plays a crucial role here. So let me tell you about that. The work of Ima, Andy, and Bruno there produces a sort of causal model of the operad BV in the context of inhomogeneous causal duality. So it's an honest co-operad for which the DG co-operad for which the co-bar construction provides a cofibrant replacement of BV. Now, so it is already lovely and allowed at that stage already to prove to prove some things about homotopy algebras, but this model is not minimal. It has the internal differential coming precisely from the fact that we're using inhomogeneous causal duality, that there are quadratic linear relations, and what Bruno and Gabriel did, they computed the minimal model, computed in some sense. So let me explain the precise sense in which it is computed. So, of course, if you take the space of generators of this model, it's a non-minimal model, so it has a differential, and compute homology of that differential, you get the Quillen homology of BV. And what Bruno and Gabriel did, they actually computed that homology and presented it as a deformation retract of that BV anti-shrink. So. this proved by Gabriel and Bruno. Has the unary part, which is the co-freq algebra and generator of degree 2, which resolves the relation delta square equal to 0 in BV. Plus the co-operad, well, I guess I can write it like that to make it more clear for our purposes. So it's a casual dual co-operad of Haikom. So it's it is clear that this result makes it clear that homotopy theory of BV can and homotopy theory of Haikom, there is an interplay that we can possibly use. But this, when I say that it's isomorphic, I mean that of course they are the same as symmetric collections. There is also a co-operad structure in both places, but in principle, the equivalent homology of an operad is a homotopy co-operad. There are some higher operations there, which vanish in the honest casual case, but in this case do not vanish. So here, when I write it like that, what is obvious on here that we have obvious co-operad structures, because this is a co-freq algebra unary part, and this is the casual dual co-operad of Haikom, so it has a co-operad structure. But this formula doesn't really tell us what are the higher operations there, and that is fairly important. So let me tell you what to do about it. Strategy is to represent, to incorporate it into a deformation retract picture, and then, okay, on the what happens on the left is that we have a DG co-operad, which is fairly tractable, which we can work with, and then the strategy that Bruno and Gabriel took was to apply homotopy transfer for homotopy co-operads and transfer the structure into an infinity co-operad structure here. So in that, and then of course you can take the appropriate infinity co-bar construction of this infinity co-operad, and this gives you a minimal model of BV. So in that sense, this was computed, but it of course relies on homotopy transfer for infinity co-operads, and those formulas get quite nasty very soon when you try to actually compute things. And so the strategy that I suggest us to take now is to leave this setup as fast as we can and move to the context of Lie infinity algebras, where homotopy transfer is a much easier thing to do. So once we have once we have a DG, say, coalgebra and a DG algebra, even we can obtain a convolution algebra from that. And similarly, once we have a DG co-operad and a DG operad, we can obtain the convolution Lie infinity algebra, DG Lie algebra, and even more so, even more if we have an infinity co-operad and a DG operad, then we can obtain a convolution Lie infinity algebra. So what is the operad with which I want to compute the convolution? Of course, it's the endomorphism operad of a vector space, because I want to construct some Lie infinite algebra where Maurer-Cartan elements have some good meaning, and if you compute convolution with the endomorphism operad, then Maurer-Cartan elements will precisely describe you the algebra structures you are hunting for. So far, so good. If you have ever seen the definition of a convolution algebra, then you can easily guess how to do things like that. So, for instance, if you have a DG cooperad and an operad, and you want to compute the Lie bracket, then you decompose, map, compose, and anti-symmetrize. If you have an infinity cooperad, then you can decompose not necessarily into two pieces, but in many pieces. And this means that you can decompose into, say, n pieces, map, and then compose in the endomorphism operad, and anti-symmetrize over that. And in the same, and this will give you a Lie infinity algebra structure. And of course, from this deformation retract upstairs, you can get a deformation retract on the level of between this DG Lie algebra and this Lie infinity algebra. So somehow, a statement which needs to be checked, but fortunately can be checked and is true, is that now you can arrive at this Lie infinite algebra in principle in two possible ways. You can either do it in the way that I described, or you can first transfer and then so you can either pass to convolution algebras and do homotopy transfer, or first pass to do homotopy transfer and then pass to convolution. And fortunately, these two ways give exactly the same result. And so what we can do now, we can almost completely forget that we shortly had to visit that universe of homotopy cooperads and just do homotopy transfer for Lie infinite algebras to compute something. And now I am almost ready to have all the parts of this main theorem explained to you, with a small gap which I now have to fill. The point is that all these formulas, of course, depend dramatically on the choice of a deformation retract that you make. So there is, and I want to argue that there is a particular choice of the contracting homotopy here, which actually, after you do all that I told you to do, will provide you a Lie infinite algebra where the Givental group naturally belongs. But of course, it doesn't happen for any deformation retract. It happens for some particular choice. And I definitely wouldn't have time to describe it in much detail, but I want to say that this choice was indeed made in that paper of Gabriel and Bruno, and it involves some rather remarkable combinatorics of trees, the combinatorial coefficients in the formulas were in a completely different context quite a while ago discovered by Jean-Louis Laday when he wanted to realize the Stashev associahedron as in some nice way as a polytope in the coordinate vector space. So let me just mention briefly that this contracting homotopy here is defined by a formula which almost looks like the coderivation of the co-free cooperad, but somehow is not quite a coderivation because it includes weights. So you do something to every vertex, but when you sum over vertices, you multiply it by some combinatorial weights. And the weights, remarkably, the weight of a vertex is equal to the product of the number of leaves on the left times number of leaves on the right, divided by the n choose 2, where n is the total number of leaves. So or is n plus 1 just to should I divide by n choose 2 or n plus 1 choose 2? I always confuse because n plus 1. And somehow this this coefficient which looked to me for a long while very random somehow turns out to be absolutely remarkable, because if you use these formulas in this particular context, if you use them to do homotopy transfer, then you get an absolutely remarkable infinite algebra structure which can be used. So let me now finally slightly alter this statement to make it precise, to make it more precise, and then make it completely precise. Is the gauge symmetry action in this algebra with the operations transferred from so the operations are obtained from this DGLA using this particular def retract that Gabriel and Bruno used to construct the minimum model of BV. So now, what exactly does that mean? Among so I already told you that the Quillen homology of BV has the part which is the co-free coalgebra on one generator, and has this part Haykom anti-Schrick. So every Haykom every Haykom algebra structure on V can be viewed as living here as the first layer of this Haykom anti-Schrick. Now, the condition of being a Haykom algebra means that in this Lie infinity algebra, this element is a Maurer-Cartan element. In fact, it is a very simple Maurer-Cartan element in the sense that this part coming from Haykom anti-Schrick. So this Haykom anti-Schrick inside the Quillen homology is a sub DG cooperad, all high operations vanish. And no, that's not what I was saying. I want to say that yes, I mean it's you can view it as an as a sub cooperad, so that is a sub yes. Inside that Lie infinity algebra, the corresponding part is a sub-DG Lie algebra, so you just have the usual Maurer-Cartan equation without infinitely many terms. And now you can take, so alpha, if alpha is a Haykom structure, can be viewed as a Maurer-Cartan element in our Lie infinity algebra. And now you can take some element R of Z in the Givental Lie algebra. You can view it as a map from this guy to endomorphisms of V, because you need to map delta somewhere, delta square somewhere, and so on. It's the same amount of information. And so now you can take not all possible gauge transformations, infinitesimal gauge transformations that you could possibly define, but only those that come from the unary part of that sort, and use that infinitesimal gauge transformations to deform your Maurer-Cartan element alpha. And the claim is that this deformation is precisely the infinitesimal Givental deformation of alpha, as we discussed before. I think it's a good chance for me to stop.
Any questions?
Am I right that you can say everything is am I right that you can say everything is same, just taking the quotient and what the quotient of d mod delta, that's subtract here this part of this. So it seems that you're just rephrasing the statement that delta is S1 is the gamology of the S1.
Well,
and the issue of delta is the gamology of the DS1 and that.
Yeah. Yeah, so in a sense, yeah, I mean, it is in some sense indeed a counterpart by result proved by Anton, by Nikita Markhayan and Sergei Shadrin, explaining that that Haykom is the homotopy quotient of du by delta. It's somehow the story goes it just goes in the opposite direction. That in a sense they used the Givental group to establish this result, but somehow which means that on High-Hom you should expect some sort of homotopy circle action, and then Occam-Razor tells us that probably it should be somehow related to the Givental action because there is already a rich enough structure on High-Hom, and then somehow it gives the Givental group. I want to say sideways related to that this construction allows to extend Givental action from acting on hypercommutative algebras to acting on homotopy hypercommutative algebras, which I think is completely impossible to do directly inside the Givental framework. So somehow this gives you an action on homotopy hypercommutative algebras absolutely for free, because you can also view a homotopy hypercommutative algebra as a certain Markov-Cartan element here. So somehow this allows to extend this further substantially.
Other questions? Okay, thank you very much.